Hello, everyone, and welcome to today's webinar with TPC entitled Understanding Multimeter Measurements for Electrical Troubleshooting. My name is Ryan Smith, your host for today, and we are joined by our presenter today, Greg Sutton, one of our expert TPC instructors, who's going to walk us through some of the best how-tos and best practices as it pertains to multimeter readings and some of the really good best practices and tricks of the trade you can follow for electrical troubleshooting during today's session. We have an hour together today, and before we launch it over to Greg, I would like to just share a little bit of housekeeping items for today's webinar. The first is that this webinar is being recorded today, and this video recording, will be made available to our website, the TPC Training website, within about 2 to 3 business days of today's webinar event. The second thing I wanted everyone to know who's tuning in is that the PDF of these slides that you're seeing here will also be available for your download on our website at that time, about 2 to 3 days after this event is over. And so you don't have to necessarily take screenshots or anything like that. I should be able to see this content after the class is over. This is not necessarily a continuing education unit type of class. It's an free informational session. So if you are looking for official continuing education, we highly recommend you take one of our TPC courses after this session is over to continue your learning and get official continuing education. And then finally, since this is a live event, let's make best use of that factor that this is a live event by asking some questions and answers in our Q&A line we see. So if you look at your control panel on the bottom of your screen, you should see a little button that says Q&A. The chat, so there's a chat. Let's try to avoid using the chat because those are hard to monitor. But what we can do is monitor all the questions and be able to prioritize them on our end to ask our instructor, Greg, at the end of today's session. So use that Q&A session. I'll monitor that for him, and we will be able to take as many questions as possible by the end of our session today. So before we hand it off to Greg, we'd like to learn just a little bit more about who's here today and who's tuning in. So we're going to ask you a couple quick poll questions to gauge your thoughts and your comfort level on electrical troubleshooting. So we're going to launch a poll right now up on your screen. So you should see a window popping up on your screen. That's asking you 2 questions. And when you see the answer to your question you'd like to provide, you just click on that answer and you'll be able to register your question to this poll question. Our first question is, how comfortable would you say you are in your ability to understand multimeter readings for electrical troubleshooting? Are you very comfortable in your ability? Somewhat comfortable? Are you kind of neutral, neither here nor there? Or are you more uncomfortable in your abilities right now? And you can be fully honest, that's why you're here, to learn, right? And second, how often do you use a multimeter on the job? Would you say you use it often, like daily? Sometimes more weekly, maybe rarely, maybe on a monthly or yearly basis? Or would you say you never right now use multimeter readings in your job? All right, we're getting some really great number of responses coming in. We're just going to give you just a couple more moments to register your responses. All right, that's a pretty good amount. So I'm going to go ahead and end the poll and share the results with everyone here. All right, so what you should be seeing is, let's see here, you should be seeing some bar charts and bar graphs showing up. And the first thing you'll see is that most of us here are kind of somewhat comfortable in our abilities to read multimeter readings. That's good. So you're here for maybe a little refresher, maybe to help you up your skills a little bit. That's perfect. And as you can see, really the experiences are all across the map. Some of us are very comfortable, some of us are very uncomfortable, which is great. This is a perfect opportunity for some learning. And number 2, how often do you use a multimeter on the job? It looks like most of us, 38% of us, are on a sometimes basis. So every week we're picking up that multimeter reading. And then shortly after that, about 32% of us are on the rarely basis. So maybe once every couple months or once a year, we're going to pick these up. But that's enough frequency for us to feel like we really need to know what we're doing when we're finally picking these up to do some troubleshooting. All right, so I'm going to stop sharing those results. That window should have disappeared on your screen. And what you can do is make sure that we have a nice full screen view of our cover slide, which says, welcome to Understanding Multimeter Readings for Electrical Troubleshooting. And without further ado, I'll hand it over to Greg. Greg, thank you so much for being here.
Thank you, Ryan, and thanks everybody else for coming too. So let's go over some of the topics we'll be hitting here. We see that the experience is all over the board, so we're going to keep it fairly simple for today, though. Things like AC voltage and DC voltage, of course, and what the how to pick the right setting on the meter, that kind of thing, and what we can do with those too. We're going to try to relate all this to troubleshooting. Resistance and continuity. That might be, probably will be the same setting on your meter, but we'll talk about the difference between the two. Also, a little bit about what is resistance, right? And what is voltage, and how to use continuity, and what does the word mean as well. And then after we get that under our belt, we'll talk about using a clamp on meter to measure current, and what that can do for us too as well. And we're not going to save these interpretation topics for the end. They're really going to be dispersed throughout the hour. What does it mean if we get zero voltage? And what does potential difference mean? One of the things we're going to concentrate on there is that your meter has two leads, and you really need to be aware of where both of them are. You can't really say we have voltage on this terminal unless you think of it in terms of, well, between that terminal and what else do we have voltage? Is it ground? Is it neutral? Is it another hot? So we'll talk about that. And what does overload really mean? A lot of people say it's overload. It's actually OL, right? It can stand for a couple different things. Overload, well, in a way it can. If it's out of limits, right, it can. How do we interpret that when we see that, when we're checking continuity or resistance there as well? And like I say, all the way through here, we're going to apply all of this right here to all the topics. We're not going to save that for the end. That's going to come in there all the way through. So like I said today, as many settings, as many functions as a meter has, we're going to keep it fairly simple. We're going to go over instead of the advanced functions, we're going to talk about AC, DC. While we're here, though, a lot of you know what these symbols are, but let's take a quick look here. If you have this, right, that means voltage on your meter. And if you see this right here, that means AC. And if you see this, it's DC. Now, some meters will automatically pick the right one. Fluke T5, for example, is one that I see a lot of people have, and it automatically picks between AC and DC. Most meters, I'd say, don't. So you have to know the difference between that. And these specs are going to vary from meter to meter, right? That'll be in your manual. For most of us, we don't have to worry about too much other than the high end, right? We don't want to use the meter on something that it can't handle. This omega symbol here is for ohms, right? Resistance, when we're measuring resistance, the ohms. Usually the same meter setting is going to have this on it, and that's just a symbol. That's an audible beeper. We typically put it on that if we're checking continuity, but in reality, it's probably a better idea to look at your meter rather than listen to it. A lot of us work in loud environments, and it's easy to miss that. It really is. You can miss that beat. And if you see something like this, it means AC or DC. So if you saw this, it would mean AC or DC amps. And if it had just that, it would be just AC. And if you saw just this, it would be DC current measured in amps, right? So let's start with the simple low-hanging fruit. Let's take a look at continuity and what we can do with it. So like I said, this will beep at you here. The word continuity means it's a complete path for current to flow all the way from one point to another. Now, this is an important thing to think about when we're talking about troubleshooting an electrical circuit, especially control, because if a circuit doesn't have continuity all the way through, meaning all the way from the source back to the source. So if you're talking about a really simple circuit like a battery, for example, all the way from the positive terminal through a switch, through a light bulb, and back to the negative, it has to have continuity to work. That's a really good way to think of it. It has to make a circle. It has to be a complete circuit. That applies to everything from something like a switch and a light in your house to PLC circuits and industrial control. It's all the same kind of thing. You have to have continuity. It has to be a complete path. So and we can check for continuity with a meter like this. We can check things like fuses, switches. We're typically looking for either a path or not. There is either a good path or there's not. Very low resistance through a closed switch or a good fuse. We should probably go to a simulation here shortly and take a look at how we might do that. So first of all, right, make sure that this thing is on the right setting. And at this point right here, with your meter leads not touching, you would expect to see OL and the ohm symbol in the display. OL in this case means open loop. You may hear it called open line, but open loop, technically open loop, and it means there's no continuity. It's not a closed loop. It's open somewhere. That's the key to remember there is the O stands for open. So we're going to test it first, test the meter. Almost everybody does this first thing, no matter what they're going to do with their meter. They put it on ohms, they put their leads together, and they hope to see something very low, like less than 1 ohm. Well, that's great. We're testing our leads. Just be careful. Don't mistake that for thinking that your meter works, right? It only means that your leads are good. That's what we're really checking. Our leads are good and that it works on resistance on that ohm scale or continuity. It doesn't mean necessarily that your meter is working on voltage. So if you're doing voltage checks, you need to make sure your meter works on voltage too. We'll get to that. So one extra little tip. You're checking when you have your leads together and you're checking for continuity, making sure your leads are okay and they're plugged in all the way and they're plugged into the right spot and you don't have any opens in your leads themselves. Shake them around a little bit, because when connections go bad, and that's what we're checking for. We're checking for a bad connection. And in the electrical world, if a connection goes bad, it doesn't usually go completely bad all at once and then stay bad. It usually comes and goes. It's intermittent. So put your leads together, shake them around a little bit. You have a better chance of catching one of those intermittent problems there. Yeah. And big thing here, if you're checking using your ohm meter or continuity, make sure the power's off. That's key, right? Don't forget that. Make sure the power's off. As far as mistakes that even experienced people make out in the field, that's probably the single most common mistake that even experienced electricians make is have it on the wrong setting. So, okay. Now we test a fuse like this right here, right? And we would expect to see something close to 0 on a good fuse, 0 ohms, and less than 1. That's a good way to think about it, less than 1 ohm. And if it's a bad fuse, it would be open and you would see OL for a blown fuse there. Yeah. So let's see if we can't put this to use. I'm going to switch screens over here to a simulator we use in the classroom a lot, Simutech. And so let's, if we're going to check a fuse, we're going to check a fuse in this control box over here. But first, we're going to turn the power off. We're going to turn that breaker off, right? Open it up, and we're going to put a lock on it. I'm going to do my test, live, dead, live. And these are all the results I get, exactly what I wanted, making sure that the meter's working, doing all the tests, and then making sure that the meter is still working on voltage. right? That's what live, dead, live is about. We talk a lot about that in, well, almost every electrical class we do. So I'm going to accept these test results. And then I'm going to open up this panel here. And check one of these fuses. So now that the power is off, all right, I'll zoom in on one of these. Now, here's a trick. I'll promise you some tips and tricks all the way through here. Here's one. It's always a good idea, if you're going to check anything in the circuit, to disconnect it from the circuit. Now, the right way to check these fuses is to turn the power off, make sure the power's off, pull the fuse out of the circuit, and check it with an ohm meter. Well, we can't really do that in simulation here, so here's the trick. We're going to take one wire off there. Okay. Now, the reason we did that is because in almost any electrical circuit, if you check just this component here, you think you're just checking it. For example, I'm going to put my meter on ohms there. I'm going to put one lead up here. I'm going to put the other lead on the bottom. But if I had left the wires hooked up, I may have actually been reading through another part of the circuit that I wasn't aware of. You think you're just reading the fuse because that's where your meter leads are. But in reality, you might be reading through anything else. And there are a whole lot of things in an electrical control circuit that you can read through. So now I know I'm only reading through the fuse. Let's check this. I expect to get something less than 1 ohm for a good fuse. Okay, that's pretty low. That's pretty low. So this is a good fuse. We could check all 3 of them. Wouldn't be a bad idea when we're in there if we're having some kind of problem. But that's how to check a fuse. Now, let's get those leads off of there. And let's put our wire back and see what else we could check in a control panel here, right? Let's see, we could check contacts. Over here, we have a contactor. We could zoom in on that thing. And contactor is just a big relay. A1 and A2 are coil. We'll probably come back and take a look at that coil after we start talking about resistance. But let's give it a try here. Let's take at least one wire off here. We'll check this middle set of contacts here. Let's see. Actually, those are aux contacts. Yeah, I'll go all the way in back and get one of these power here. So from 1 to from 1 to 2, it should be open right now. So we expect to get an open reading like this. Yeah. And then we push this in, the contactor is closed, and we're getting less than 1 ohm. That shows us that that set of contacts is in good shape. They're good. And this is something that does fail if you're having problems with a motor tripping overloads or something like that. This is not a bad thing to look at. This is something that does go bad, the contacts within the contactor itself. And of course, you check all 3. What you do not want to do is try to start a motor by pushing this in like this. We're only doing this because the power's off. This is important. I know out of the 246 people we've got listening to this, probably 245 of us have done it, right? Push that in to see if the motor starts. And from a troubleshooting standpoint, it makes perfect sense. If we push that in and the motor runs, well, we know the motor's okay and the contactor's okay. And we have 3-phase power and we don't have 1 fuse blowing ahead of this. Well, the problem is, think about it like this. What if the motor was shorted out, right? If the motor had shorted windings and you push this in, well, what you're creating is a phase-to-phase short circuit. You're bucking phases. Most of us are dealing with 480. 480 phase-to-phase, there's going to be an arc. And where's that going to happen? Right here where we are. So remember that one, please. So I'll get my meter leads off here, and I might as well put this back. Good to not take too many wires off at the same time. Yeah, I'm having a hard time with this. Maybe I can zoom in a little. There we go. Okay. All right, then let's back out. And let's check a push button over here. Here we have a push button. We'll zoom in on that one. Yeah, take this cover off. And again, we're going to take some wires off because we could easily read through something else. Yeah. Matter of fact, let's just try it. It's worth trying this real quick, right? Yeah. Try to get this. Let's do take one off like this. Here we go. Yeah. Okay, put it on ohms. Now, everybody should be thinking to themselves right now, well, that's a close button and it's green. It's probably normally open. And you'd be right. We expect, right, to get an open across this push button right here. Momentary, normally open, momentary push button. And it is. And if I push it in, well, we get something close to 0. So that's good push button there. Yeah, that one's good. That's good. So let's put that back together and try that stop button. So everybody should be thinking at this point, if we have, if that was normally open, if this is normally closed, we should have continuity across this one. Okay. And let's try it and see. There we go. And we expect there to be 0 ohms, something very close to 0 ohms across this when I drop the lead down. And that's what we get. Yep, we're getting 0 ohms. It's already closed. We would say there is continuity between those two contacts. And if I push the stop button, we should see it go open. And there it is, open loop, OL, open loop. Yeah, yeah. And I mentioned before, but this can mean out of limits. Let's say you have it on the ohm scale and you put it on 120 volts. Well, that's out of limits. You'll probably get OL there. Yeah. Or if your meter's good for 600 and you're checking 700 volts or something like that, then yeah, it'll be out of limits. Okay. All right. Let's put it all back together. And we'll go back to the main presentation there. Okay. I'll get you guys back over the right screen. Here we go. Okay. Now, resistance. What we've been measuring up to this point is very low resistance, right? Very, very low resistance. We would say it has continuity. But like things like copper wire, have very low resistance, right? Well, just to define resistance, it's the opposition to current flow. These electrons are trying to flow through a conductor like copper or something like that. And there's resistance there, and resistance impedes the flow of those electrons. So our readout is measured in ohms. There's the omega sign we've been looking at. And a lot of ohms would be high resistance. Low ohms would be, very little ohms would be low resistance. So all materials do resist current flow. It's just that copper and aluminum don't resist it very much. And things like, and we call those conductors, right? Silver, copper, gold, aluminum. And then something has a lot of resistance, we say is an insulator. Like, for example, rubber, paper, glass, plastic are all good insulators, right? Right. So if we're going to measure resistance, we do it the same way as continuity. We're just expecting different numbers is all, right? We expect a certain amount of resistance. Again, first thing, turn the power off, right? Make sure we turn that power off. Okay. We should at that point, right, see something like OL, and it might say M ohm for meg, because again, air, right, between the two leads is very, very high resistance. So it's going to show open loop and probably meg ohm, many, many ohms, millions. So, okay, again, pull the component out of the circuit if you can. If you can't, take one wire off and then put your leads across it like this. Here, we're measuring the resistance of the coil of the relay here. Now, another tip. We don't know how many ohms. You see here, we're reading 74.6 ohms. We don't know how many ohms it was supposed to be without a spec sheet or something, but here are two things we do know. It shouldn't be OL, because that coil in there, that would mean it was open, right? So that coil in a relay or a starter shouldn't be OL, but it shouldn't be close to zero either. If it was close to zero, that would mean really close to zero. That would mean that it was shorted, the coil was shorted. So even though we don't know what it should be, we know it shouldn't be OL, and we know it shouldn't be close to zero. Now, here's another trick, right? Another tip. A lot of people, I know those of you who answered the poll saying you use a meter every day, I'll bet you've been fooled by this. Let's make sure maybe everybody else doesn't get fooled by this. Look closely at that display. What is it? Does it say ohms or K ohm? Here, let me zoom in on this, show you the difference. Look at these two measurements. They both look pretty close to 74 ohms, don't they? This is how you get fooled. Look closely at this one on the bottom, and you'll see K ohms. So this measurement here, K, is 1,000 times different than the one above it there. One of them is 74 ohms, this one, the top one, and the bottom one is 74,000 ohms, K. And that's K for 1,000 and M for 1,000,000. So it is really, really easy to get fooled on that, not just on continuity, but also voltage as well. Yeah. So if we measured these, good light bulb, bad light bulb, coils or relays, things like that. Yeah. How about this one? What would that mean? So of course that's a bad coil, open coil, assuming we're on the right lead, in the right place there. A1 and A2, yep, I think we've got a bad coil there. Yep. Okay. So let's go back to our simulator and check that one right there. Let's go check the coil on that contactor. Now, let's see, power's still off, it's locked out. Is it locked out? Yeah. So let's zoom in on this control panel here again. And there's A1 and A2, just like on the relay we looked at there. Since this is the kind of thing we can't just unplug from the circuit, like fuse, I'm going to take one of these off and check across this coil. Now remember, we're asking ourselves the same thing. What do we expect to get? Well, we don't expect to get zero, and we don't expect to get OL. By the way, here your meter leads, the color of your lead doesn't matter here, right? Black and red doesn't matter. Later on it might. Okay, there we go. We got 82 ohms. That's reasonable, right? That's reasonable. Okay. It will be really different from one relay or one contactor to another, one coil versus another coil. But in almost every case, it shouldn't be zero, and it definitely shouldn't be OL. Yeah. Okay. All right, then. Let's go look at voltage. So voltage is the pressure, okay, in a circuit. If you think of it as a water system, like we said, voltage is the push. It's the pressure that allows it to go through. The flow is current. So you can't have any flow without pressure, which is the same as electricity. You can't have any current without voltage, right? So the voltage gives us our push to get something moving there. DC is direct current. That means the electrons, the current is only flowing in one direction, right? Like a battery's DC. Yeah. AC is alternating 60 times a second. Here in the United States, it's alternating the direction, right? We call that the frequency. The frequency. How do we measure DC? So again, look at the symbol there, right? Make really sure. And hey, people, as far as mistakes that you can make with a meter, this is probably the single most dangerous mistake that you could make with a meter like this, having your leads in the wrong jacks. It takes longer than we have here to explain why that is, but that can end up going very, very badly for you. There should be a decent meter is going to have a fuse in there, but even that quality OEM fuse can only handle so much current. And if you have your leads in the wrong jacks, like for amps over here, and you go to measure 480 volts somewhere, well, it could end up being very bad. Maybe just blow the fuse. Maybe your meter explodes and you create an arc blast. So make really, really sure you're in the right jacks when you're measuring voltage. So just put the dial on DC volts as we said there, right there. Now you do have polarity here, right? So now the red and the black leads do matter, but if you get them wrong, the only thing that'll happen is you'll get a negative sign there. You'll just get a negative sign. Here we have red on positive and black on negative. So we see 9.62 volts. Again, watch that V. It is really easy to measure something that has no voltage at all on it, and it's still coming up as millivolts. Matter of fact, it's just uncanny how often it comes up to something around 120, but it's actually millivolts. It's not volts, especially AC. Not as much on DC like we're talking about now, but it does happen on AC. Keep an eye on that display. Yeah. So AC volts, not too hard. Make sure you're on the right setting. Make sure your leads are in the right jacks. Again, right? For most of us, this is the most dangerous part. We're on AC. We might be on higher voltages. We might be on bigger equipment, and having those leads in the right jack is really important. Really important. So look for the AC symbol there, right? And put your leads on. Put your leads on there, right? AC doesn't have polarity. You don't have to worry about red and black there. Right? It's AC. A couple other little tips. It seems like it's obvious, but don't touch the metal. Don't keep your fingers off of the metal part of the leads there. Yeah. If you can use if you still have your caps that go on these leads and just have a little bit of metal hanging out, right? Just a little tiny part of the lead sticking out, that's safer. It is safer, yeah. And it's really easy, especially troubleshooting on terminal strips, to have these touch each other, right? You have two leads down on two terminals and they touch each other. Again, a lot less likely to happen if you put on your caps. Yeah, go on there. Okay. So let's go check some AC voltage here.
All right, so you should see a taking multimeter readings module on your screen now. So what we're going to see here in this circuit is a more basic circuit, but it still has all the fun components. We got a push button that you can press. Lights are on, lights are off, lights are coming on, lights are coming off. So if we're going to test AC voltage in this case, which is what's next on our agenda, which one do we want to touch, right? What did Greg say? Was it the one with the flat lines or the one with the squiggly lines, right? Well, alternating current at the 60 hertz is this right here, the squiggly line version of the voltage reading. So what we're going to do is drag this over. A really good place to start is in terms of any electrical troubleshooting steps is to start from line to neutral. So let's take black, put it on neutral, take the red and put it on line. Again, the whether it's red or black on either one doesn't matter because there's no polarity here. And in this case, this is a 115 volt control circuit. And how do we know that? Well, if we looked at the schematic, the control schematic would tell us 115 volts AC is what we're looking for. And turns out that's the case. Now, here's an interesting one. What would you expect to get if we put the red lead on this part of the fuse? We tested top to bottom of a fuse with ohms earlier in this session, but what would we do if we tested left to right of this fuse in voltage? Should we expect 115 volts from 1 to 2 across this fuse right here? What do you think? Well, let's see. 0 volts. Interesting. Why are we getting 0 voltage across this fuse? Well, that really starts speaking to the nature of what voltage is and what we're actually measuring when we get a voltage reading. Voltage is not telling us, and this is kind of back to the question Greg posed at the beginning, does 0 voltage mean our circuit is de-energized? And in this case, the answer is no, that is not necessarily what it means. If we're getting a 0 voltage, that's not necessarily telling us that the circuit is de-energized. What it's actually telling us is that the circuit is experiencing no potential difference from this point to this point. So from point 1 to point 2 or point A to point B. So that's the real thing we're measuring is potential difference. So did the electrical energy we're seeing inside of these wires, that push for the electricity change from this side of the fuse, from this side of the fuse to this side of the fuse? And the answer is no, it's been just as live and high potential from inside to outside of the fuse. So the difference between high potential on this side and high potential on the other side, the difference between those two potentials is 0 because they're both high potential. Now, if we went from high potential on this side to low potential on the other side of the fuse, then we'd see a voltage, which would mean what? Well, that would mean that the fuse is probably blown or is bad, right? If we go from high to low and we get 115 volts across the fuse, that's a really good indicator that the fuse is blown. Now, does that mean the fuse is bad and just needs a replacement? Probably not. A really good rule of thumb here is that if you are dealing with a blown fuse, usually the final answer to solving and troubleshooting that problem isn't just to replace the fuse and start the circuit back up again. Usually there's something causing that blown fuse, whether it be something in the circuit's drawing more power than is safe, or we're exceeding the amount of horsepowers we're drawing on the motor, or something else along those lines. One more example of measuring voltage is going to be from neutral to ground, right? So we should expect what in terms of voltage between the neutral, or what we call the grounded, the National Electrical Code will call the grounded conductor, and the ground? Well, what should be received is right here, neutral to ground, 0 volts. That's good. That means our neutral, our white wire, in many cases, is attached or directly connected to that ground. We want to see 0 voltage to ground. Now, if for any reason we ever saw a voltage between neutral and ground, that means something is not quite right in terms of the direct connection between neutral and ground. So that can help us as well. One of the trickiest parts of electrical troubleshooting becomes when we start measuring a voltage across a neutral, from one part of a neutral to another, and starting to see that there's some discontinuity or some voltage buildup on a neutral. Just gonna check in. Okay, yep, Greg, I think we've lost him, but that's okay. We're gonna keep going without him. One more thing we're gonna talk about before we start getting to the Q&A. By the way, it's almost Q&A time, everyone. So we got a few questions showing up. Feel free to pose your Q&A in the Q&A box, and I'll be able to answer as many questions as possible. Tag team this with Greg here. So AC voltage we're on the topic of. What we're going to do in this scenario is I'm going to go to our main menu of this particular one, and we're actually going to get into a troubleshooting scenario. Troubleshooting scenario 1, I actually already talked about, but let's walk through it real quick. I'm going to take us to AC volts. And first of all, let me press these green buttons again. Pressing the button, nothing's happening. I'm pressing this button, nothing's happening. How about the second button? Okay, third button. Okay, something's not quite right here in this circuit. These lights won't come on, nothing seems to be working quite right. What could be happening, right? So it's time to take our meter. Our eyes and ears have only told us so much. Now it's time for us to see what the meter tells us. So from line to neutral, like we did before, we're getting a full 115 volts AC. What that tells us is that we haven't lost power to this circuit. We're actually getting a good power coming into this panel. So we know the issue is somewhere inside this panel. Let's go and move this red lead, and let's slowly trace this red lead down the main line. What we always say is the two most important tools for anyone doing some electrical troubleshooting. The first most important tool is not a hammer or a wrench or, you know, a monkey wrench or anything like that. The first and most important tool is the multimeter right here. So we're already talking about that today during the webinar. But the second most important tool you can have, again, is not something you might typically think of as a tool, but it's a schematic. So if you have a meter and the schematic, you can pretty much do anything when it comes to electrical troubleshooting tasks. So let's take a look at that schematic. Well, what our job is to do is to hold the black lead against neutral and to slowly trace the red lead through this circuit and see when that 115 volts potential difference changes from 115 down to 0 when we might not expect it. So we're going to start on the top side of this fuse, and we're going to move systematically to the bottom side and then in over through these push buttons until we get something we don't expect. So let's go to the bottom of our line terminal board. Still 115, still feeling good. So we're up here. All right. We're going down to terminal 1 on the fuse. We're still at 115. You know what that tells us? That means the potential is properly carrying itself on that wire. So we're feeling good. Let's go over here to this one. 0. Uh-oh. So we went from 115 on this side of the fuse to 0 on this side of the fuse. That's really an indication of that fuse being bad. And like we talked about before, if we were to put the leads on either side of this fuse right now, 115 volts is that reading we're getting, which means we're going from high potential to low potential on that fuse. And since this is, a control circuit, this is fine. You want to avoid measuring from top to bottom of a fuse in a 480 volt, let's say 3-phase system, because if that overload is to be happening on the high voltage, your meter can actually be the new path for current to flow. So I know someone was asking earlier, why do we want to remove a wire from the fuse? Well, that's really it's really true. The best way, the most foolproof, safest way to test a fuse for continuity is to pull it out of the circuit. There's no chance that anything else can be getting in your way while you do that reading. But in the case of the simulation, we'll pull the wires off and that will give us the same effect. All right, so let's do this next troubleshooting one, which represents something new but related to what we talked about, and then we'll take questions. So here's the same panel, right? And it's the same kind of symptom. Nothing's happening. I'm trying to start this stuff, nothing works. Well, let's go over to the meter. Let's do our line to neutral test again. Here's line. Here's neutral. 115. Okay, that's good. Let's start systematically moving. 115. 115. And aha, we're still at 115. So the fuse is seeming pretty good. Let's go down to here. Next one is the input. Again, I'll look at my schematic and I'll see the terminal number 1 on either one of these push buttons will be the next thing off the main line. We see 115, which is good. And on the other side of the button, oh, it's 0. But if I press the button, oh, now it's 115 when I press the button. That indicates that this green push button is doing its job of closing the path and allowing us to have voltage on the other side of that button. So we trace, push button 6 is next. So we go over to here. We see that push button 6, terminal 4 is next in line. And I push the button. Push any one of the buttons, in fact, or any of these, right? It's going to give us what we want in terms of 115 volts, which is great. On both sides of push button 6, push button 5, yes. Push button 4, again, we push all 3 buttons and we're getting the same thing. We're getting readings we would expect to see all the way through, but still the lights aren't coming on. We're getting closer, I think, to our answer. Now we've gone through all 3 of these buttons. Let's do terminal 2 of the relay. That's terminal 1. Let's go over here. Pressing the button and we're getting 115 volts. We're almost there. Let's do terminal 7. All right, 0 volts. Press the button, it's still 0 volts. Now that might make it seem like something happened to the coil. However, that's not necessarily an indicator, because neutral side of the coil, which is 7, and neutral itself, there shouldn't be a potential difference there because they're on the same line. So really what we have to do in this one, because the whole story is not being told with voltage, the coil could be bad or it could be good. It really depends, but it's a possibility for this coil to be bad. So let's go to our circuit, shut it off like we did in the other simulation, lock it out, verify. And do you guys remember what Greg said? If we went across a coil, what the reading should be? Should it be 0? Should it be OL? Should it be somewhere in between? And the answer is the correct reading for a mechanical coil of a relay should read some resistance. It should read, 60 ohms, 70 ohms, 10 ohms, 30 ohms. It really depends on the make and manufacturer, but it should read some ohms from 2 to 7. Let's see what this one reads. Aha, OL. So we're disconnected from the circuit. We're reading nothing across this coil. That has told us a story that this coil has been blown out of this relay. So what we can say is, all right, continue to our assessment. Select the component you want to replace. Click here. All right, I'm replacing the relay. Now, should I replace the coil or the contacts of the relay? Well, we just discovered the coil is not right. So let's do that. We just replaced that coil. Now let's see what happens. Now we're happy again. So really, troubleshooting takes practice. It's a systematic approach, but understanding these meter readings as far as voltage really can take you the whole way across the understanding of knowing where you need to go for these electrical troubleshooting readings. So what I'm going to do is, let's see, stop here. And what I'm going to actually do is stop sharing my screen. And what I'm going to bring up a little info slide as we get ready to answer some questions. So I'm seeing lots of great questions coming in on the Q&A line. So let's see what we got. The first question on the Q&A is meter ratings. That's a really good question. We're talking about categories, right? Meter categories. We didn't really talk about them in detail, but I would just say if you want to get all the most detail on different meter ratings and how to do an inspection on a meter, come to one of our Flash Electrical Safety or Electrical Troubleshooting 2-day classes. We really have all the different meters that we play around with, and we get to inspect them for the usage. Essentially, the higher the category, the more safe you are and the more protected you are from voltage transients and abnormalities in current. So category 4 can be used in places that have very high potential or very high maximum fault currents that they could see. And those are outdoor applications near transformers. As soon as you get down to category 3, you're dealing with stuff that can only be used indoors, but it can be used on pretty industrial 600-volt rated equipment. And then 2 and 1 are really for a 208, 240 maximum voltage in more branch circuits, kind of receptacles and small tabletop equipment when you get down to category 1. The important thing about the categories, these 4 categories, is that you're only as good as your weakest link of your multimeter system. So what we mean by that is if you have a category 4 meter, right? The meter says category 4, 600 volts or whatever it might be. But then you look at your leads, your red and black leads, and they're rated category 3. Guess what? Your whole meter system now is only category 3 because your leads can only get up to category 3. So you should try to avoid going out. You should absolutely avoid going outside with that meter and those leads because the leads can only be used indoors, for instance. So I hope that helps answer the question about ratings. There's a lot more detail behind ratings and underwriter's laboratory listings and voltage ratings and visual inspection on multimeters that we get into more detail in our class. Is it possible to get that software we saw for the simulation, that 3D simulation? Absolutely. So all the stuff we've been showing you today is available for continued learning after a class is over. What we like to say is that these can be utilized for continued practice and on-the-job kind of practice in a safe environment, right? You can actually get yourself seriously shocked in these simulations. And that's a great learning experience in the simulation that you don't necessarily want to have to put yourself through in real life. So there's really a good place for these to do some hands-on learning for employers to verify, let's say, the skills of their technicians. So just keep that in mind. These are all available. The one you guys saw was a troubleshooting motor circuit. You saw that there's a motor attached to the top of that garage door. There's some other ones with more control circuit stuff like relays. There's one with a series of relays where you have a safety gate that has limit switches that get engaged, and you have to try to get the password to be correctly programmed into this control circuit. That's a cool one. There's another one with a variable frequency drive. It's one of our newest ones where you're actually powering an industrial process with and again, you have the multimeter and you got to do electrical troubleshooting, but it's a variable frequency drive. You can run the system faster or slower and program that drive and get to see the different settings and try to figure out what's going on. Each of these simulations have dozens and dozens of faults, so you never really know which fault you're going to get, and that's really good to test your skills and for you to test your technicians' skills in your department. Why is it better to remove the wire? I think we talked about that one. It's just so that any of the feedback or noise in the system is removed, and you're just testing that fuse at that point. Is there a training session on these topics that's even more beginner than this training? Absolutely. That's a really good point. We really jumped into these live electrical panels. Basics of electricity class is the one I would draw your attention to. Basic electricity for the non-electrician, look into that. We'll have information on that. Motor troubleshooting, this is a good one too. Can you walk through the motor troubleshooting process? I wish I could in only 5 minutes, but I would say that when it comes to motor troubleshooting, make sure you have a category 3 meter and that the motor is completely either. So what we say in terms of troubleshooting motors is, if at all possible, make sure you can do some of the electrical tests on this motor when it's completely disconnected from electricity, right? If it's live, there's all sorts of things that can go wrong in terms of opening that junction box for the motor while it's still hooked up to live electricity. So the best electrical test you can do on a motor to test its function electrically is Megger, right? A megohm meter, which can measure millions of ohms. And there's actually a bunch of really cool things you can do. In fact, I think I can bring that up for you right now. We got a smaller simulation on taking megohm meter readings that I'll show you that we like to use in the classroom. Let's see, resume. Yeah, here it is. I'm going to bring it up on my screen right now. And this one, basically the magic of using megohm meters for your use. So if you have a motor, let's say 4 different motors you're going to test electrically on the workbench, and you take a look at any given motor, using this tool correctly on getting into the junction box and attaching your alligator clips and really knowing what readings you should be getting for ohms on this setting, or mega ohms, and pressing the test button on this setting between phase and ground, and getting these readings and understanding what they mean. You practice that in a class for sure. And there's a lot behind it. There's NFPA 70B has a lot of best practices on how to troubleshoot motors and what to look for from the readings for mega ohm meter tests. Let's see, will a certificate be available from this webinar? Unfortunately, since this is a public free session, official certificates of completion or attendance aren't offered for this webinar. But if you do want an official attendance certificate for training, I say definitely take one of our official 2-day trainings. So it couldn't recommend them enough, obviously. Let's see, if an HVAC compressor is shorted to the ground, right? How would the multimeter read? And this is actually to really find a ground fault. What you're seeing here, this could be a compressor motor for all we know, a 3-phase motor. Looking at the metal housing with one lead and one of the phases of that motor with the other, and we do the mega test with the testing button, and we get a reading that's less than 5 mega ohms, or something just small enough that this mega ohm reading is small, that starts indicating we're getting that ground fault circuit issue there. So I know we've got a few more questions to answer. Unfortunately, I won't be able to get to them all, but let's see if I can try to answer a couple more. And I think this mega question really helps knock out a couple of your questions. Mega ohms, yep, what's the best way to test for a direct short? That would be ground fault would be using mega ohmmeter. If one of the phases are starting to touch the metal enclosure, that's for mega ohms. To test for any other short, we say ohms with the power off. So again, the closer to 0 ohms you have between one spot and another, the closer you are to having a direct short from that one part to the other part. Can these simulations be custom made? Great question. We have a lot of content designers and developers at TPC. Yes, the answer is yes. We can do, like this thing you see here, we've custom designed these for customers before. Create more interactive exercises or more full simulations, 100%. And how can we go about taking a 2-day class to get certified? Check out tpctraining.com. So that is our website. I unfortunately wasn't able to get that up on the screen for you, but you'll see all of our credentials at tpctraining.com, where you can call us, you can email us at sales@tpctraining.com. Take a look at the catalog, take a look at the simulations. Feel free to get in touch if you want to get free access to these simulations to check out for yourself, and to really start getting practice for yourself in these simulations. So that's about all I got for you today. Our hour has already passed. That time really went by so quickly. So it's great to have you all here. Thank you so much for tuning in, and have a great day.